Good morning everybody. So, we will give one more lecture recalling the trace theorem, because we will be using the trace theorem in the weak formulation. So, trace theory basically. So, trace theorems are important because when you are have functions in a function u in L2 of omega, L2 of omega functions are defined only almost not for more than that, even LP of omega. The functions are defined in an almost everywhere sense. That means that if the two functions f and g are equal almost everywhere, then f and g are regarded as the same function. So, it is like an equivalence class. Since the boundary of omega, if you take a boundary of omega, the d omega has measure 0, the Lebesgue measure of d omega is 0. So, one cannot restrict, there is no meaning basically immediately, one cannot restrict u to the boundary immediately, at least in a reasonable sense. Same is true with when same is true if u is also in the Sobolev spaces, so W1P of omega. But you are going to deal with the boundary value problems. When you are having a boundary value problem, your boundary values are assigned on the boundary. That is a serious issue. So, how do we interpret? So, you need to interpret, because if it is a classical solution, for example, for an equation thing, if you are looking for a solution in a smooth class up to the boundary, if continuity is there, you can restrict u to the boundary. But you are no longer working with the boundary value problems. You are going to work with the boundary value problem, but you are not going to work in a smooth space. Rather, you are going to work in Sobolev spaces. These are all the issues, and that is why how do we interpret u if u is in W1P of omega. So, let me write it, let me state the theorems, then it is more complicated when you go to W1P. So, let me restrict to H1 or HM spaces. If u is in H1 of omega or H1 of say, yes, H1 of omega, how do we interpret u is in, how do we if u is in S7, how do we interpret u restricted to the boundary of omega. So, okay. So, I will write the general theorem for omega, but when omega is Rn plus, you can have the you can have an you can prove the results, how to restrict and all that, and you can prove the results using Fourier transform, which we have done in detail in the last course. But so, let me recall that one. So, if you have u is in if you have your H1 of Rn plus, the theorem I will state it more clearly later. If you have u is in H1 of Rn plus, d of Rn plus is not dense. So, you use the density results. You see d of Rn plus is not dense in H1 of Rn plus. H1 of Rn plus is this one, okay. Yeah, we will go to that one, but you still you can approximate by smooth function. So, you take C infinity functions on Rn, then if u is in a C infinity function in Rn, then you can restrict u to the boundary of Rn plus, you see, because of the smooth function. So, you do that one. Of course, C infinity of Rn functions need not be in H1 of Rn. So, probably you have to work with C infinity of Rn and H1 of Rn plus. So, if you have these functions, C infinity functions belongs to H1 of Rn plus, then you can restrict u to, so and these points here can be associated as x prime 0. So, a general point is x prime x n and the boundary is full R n minus, that is the point where you can apply Fourier transform immediately. The whole, this is R n plus, which you know. So, you can define u x prime 0, okay, that you can do it immediately. And then what you can do once you know this u, so if you define u, say if you call it this is equal to w x prime, this is a restriction of u, but starting with u here, and then you can actually show that that belongs to L2 of R n minus. You see it is on the boundary. So, the continuous functions in this restricted to that, it is in L2 of R n minus, you can do that. And you can have an estimate this w or u of x prime 0 L2 of R n minus is bounded by constant into your norm u into h1 of R n plus. You can do that. So, you have your continuity. So, the restricted functions you have the continuity, and this is dense in h1 of R n. So, you see that is what you do it. This is dense in h1 of R n plus. So, every function in h1 of R n plus can be approximated by smooth functions, but not compactly supported functions in R n plus, but not compact in R n plus 1 functions. And with this inequality, now you can extend. So, you have on a dense set, you have a function and you have a continuity estimate that gives you, you can extend u. You can rather, because by density now you can define u in h1 of R n plus, you can define an operator, it is not point wise. So, you have a linear operator, you see this is a previous one is a linear association. So, every u in this space you restrict here and which satisfies this estimate. So, this estimate is very important. Once you have a continuity estimate on a dense set to h1 L2 of R n plus, by the continuity you can extend there. So, you can define an operator gamma naught of h1 of R n plus linear operator to some space L2 of R n minus. So, keep that the gamma naught of u is not point wise thing, though in practice we always write u. We may not write gamma naught of u all the time, but when you write u restricted to the boundary, you have to understand it as the boundary values in the sense of trees, and then you can also prove gamma naught of u in L2 of R n minus is less than or equal to constant into norm of u in h1 of R n plus. This is just Fourier transform is enough, but you can prove more results, not this, and this I will write it general omega as soon as I finish this. For general, more results, not just one, more results. Each one requires a proof. This is the first part of this thing, and the second part you can actually show that gamma naught maps h1 of R n plus to h half. This is where the difficulty when you go to bounded domains. So, I will not have time here, but here the boundary is R n minus, and hence this is defined via Fourier transform. You see, it is already defined via Fourier transform. But when you have a boundary, I will just give some intuitively give some ideas how to define h half of d omega, and then you can show that continuity with respect to that h half norm is of gamma naught is bounded by this one is continuous. And more than that, you can actually prove gamma naught is onto. That is very important to again to prove the boundary value problem, because every function f given in h half of that is how your boundary value problem will be dealing with. So, that can be extended to get a function here gamma naught here. And the third part is more interesting, what is kernel of gamma naught? Kernel of gamma naught is nothing but h1 naught of Rn plus. And this is very interesting in the sense that, so if gamma naught of v equal to 0, that gamma naught v can be approximated by drn plus 1 functions. Okay. So, these are all we have discussed already and given the proofs in the last set of lectures. So, let me write it here. The same thing can be extended for other domains omega. So, we will be, so if you have, so the general theorem you can write. So, you need omega of class Cm and you can have more results. So, you need more and more, not only u can be restricted, if you have h2, the gradient u will be h1 and the gradient u will also be restricted, and which will allow you to define the normal derivatives. Once you know the grade u restricted to the boundary, you can do the thing. So, that is what I am saying. So, there are trace maps depending on the smoothness of the domain. So, then there exists trace maps. I will put it in one stock everything, a gamma which is gamma naught, gamma 1 etc. gamma m minus 1. This is mapping from Hm of omega to, so each one L2 of boundary of omega. You know how to define the using the surface measure etc. L2 of omega to m, okay, such that it satisfies everything. One, its image, what is this such that gamma naught of v is v restricted to d omega if everything is smooth. If it is smooth, it is the same restriction. Otherwise, it is as an operator you have to do it. Gamma 1 of v is equal to dv by d nu restricted to the boundary such that gamma m minus 1 of v is equal to d power m minus 1 v by dv power m minus 1 restricted to the boundary if v is smooth. V is smooth appropriately, okay, to restriction. For example, it is an m, so you need the differentiability up to that, okay, and then it satisfies also this condition. For example, v is in C infinity of omega bar, then you can do this. So, if you have the smooth functions up to the boundary, you may not require C infinity for xcm of omega bar will do that one. Okay. So, you can do that boundary case thing. So, and then exactly like you can write your range of gamma. So, each time I already told you from h1 you got h half, that means it only reduces half. So, each time it will reduce half. So, you have your range will be h minus of m minus j minus half. This is important thing to understand, product of j equal to 0 to m minus 1. So, when j equal to 0, that is gamma naught of v will be m minus half. Gamma 1 of v will be m minus 1 minus half m minus 3 by 2. All these each time for a derivative you take, you reduce one derivative. For restriction, it will lose half derivatives. Okay. And that is one thing, it is and it is onto to this space. So, range of gamma is that one, and then the kernel of gamma is nothing but HM naught of omega. Okay. So, that is what you have. So, in particular, if you have H1 naught of omega C1, then this is nothing but set of all V in H1 of omega such that gamma naught of V equal to 0. So, in eventually in the main lectures we do not use the notation gamma naught. I am repeatedly telling this, but we write only in this sense. So, it is such that V equal to 0 on d omega, you see, on d omega. So, for omega C2, then you can have H2 naught of omega. These spaces at least we will be using, higher order we may not use it, H2 of omega such that V equal to dV by d nu equal to 0 on d omega. You can write this. So, okay. So, we will do this one or that one. So, for example, if V is in H1 of omega, for previous case you have gamma naught of V, that is V restricted to d omega, if smooth, otherwise is the, we write all these notations. This is in H half of d omega. If V is in H2 of omega, that will imply your V is in V restricted to d omega is in H3 by 2. So, you can solve such boundary value problems, you need these conditions, these spaces. So, let me give you some idea. The defining fractional order Sobolev spaces itself is a difficult thing, but at least for the gamma, say for example d omega with bounded domains with the compact, let me give you some intuitively how do you do this one. This is again about the way you omega is smooth, right. So, omega smooth, that is important. So, say C1 in this case. So, what you basically do is that you can using the compactness you can cover this by like this. Okay, you can do that one, and maybe you can put another to eventually to get a partition of unity. So, this is will be your U1, U2 like that. This is a thing, and this may be your U0. So, use that, and for each thing you can go to, this is how you have defined it, smoothness. Smoothness means there exist neighborhoods U1, U2 etc., which will cover using the compactness with the finitely many. So, there will be a map here, you see, this is your Q, and then this is your G map, and then you have your partition of unity psi j, partition of unity. This is one of the easiest way I can define for that, partition of unity, and then you can write your U as summation of psi j of u, and you know that the support of psi j is contained in all that, use it, support of psi j is contained in uj. So, you have your uj will be here, the psi support of psi j uj will be here because of these quantities also, you see. So, support of psi j u, uj is open, is contained in uj, you can do that. So, using this map you can define, so it is defined here also. So, you can take this boundary value. So, start with u is in smooth, then you extend it, that is enough. So, you have your u and then you take this u here via g here. So, you will get g of psi j of u basically this is, and then you once you restrict here the boundary because of the compact support, the support on this restriction. So, you look at your g of psi j of u, it is only restricted to x prime 0, you see. So, it is here, and at the boundary it is 0, it is 0 here. Since it is 0 here, you can extend here by 0. So, you see. So, you can extend, you can actually define g of psi j of u tilde. Okay. So, you demand this to be in h half of r n minus, you see. Okay. And then the way thing it should happen for everything, all kinds of partitioning. If that happens and if you have h half of r n minus 1, we basically say u is in h half of d omega. This is the one way of viewing the restricted boundary. But then there are different ways of defining fractional order Sobolev spaces. Probably you can see Adams or something like that, maybe other spaces. It is not very easy to define fractional order Sobolev spaces. Here we can use somehow manage using Fourier transform. How do you get that? Because you can't define the half derivatives directly. So, the Fourier transform somehow allows you to do that. Okay. So, you can not only h half, you can define whatever it is. You can. So, if hs, you can define that. You can do that. Okay. That is the way to be defined. So, let me recall one of the important thing discussed in the previous part 1 of this course. Just let me recall the integration by parts formula. This is the, so I want to see which are the formulas which we use now. Okay, integration by parts, I will quickly recall. And then I will stop this review article. So, again what is integration? Omega is of class C1, and of course you need what is called, I will not discuss it, where you are, when you move along the boundary, the sides along the same side of that, what we call it basically the orientability. So, let us not get into all that, that are all technicalities of the proofs, okay, even for the classical thing. Then integral di of u. So, for v di of u, v, this is a distributional derivative minus u di of v over omega plus du by d nu, no sorry, it's not du by d nu, that is the next step. U means it is a boundary. So, first time let me do it gamma naught of u, gamma naught of v, nu I, the ith component of the normal derivative with respect to the surface measure. So, this is eventually we write it as like this, u v nu I d sigma. Okay. So, we will do that. So, this is what the formula we will be writing, we will not write gamma naught of v, and this is true for all u v belongs to h1 of omega. This formula you should remember all the time. Okay, we will be using left and right this formula. So, in fact, the Sobolev spaces, many things I got motivated last time. using to which an attempt to understand the integration by parts. In particular, if the trace values are 0, that if uv at least one of them is in h1 naught of omega, that implies integral of di of u v dx is in omega is equal to minus, you can interchange. You can take the derivative to the other one dx. So, all these formulas are again we will be using plenty. Maybe some useful identities derived from their useful identities, and these identities we are again straight away going to use for our thing. So, suppose uv is in H2. So, what we can do if u is in H2, di of u is in H1, di of u, di of v is in H1. So, that you can take di of u, so take di of u instead of u, because di of u is in H1 of u. So, what will happen in this one? So, you can take di of u here, di of u, that's and then sum it, and then sum it, because what is di of u? Summation is nothing but your Laplacian of u. So, you will have integral of Laplacian of u over omega over v. On the right side you have di of u, u di of v. So, di of u dot di of v, and sum it, this is nothing but grade u grade v over omega, and here you have instead of gamma naught of u, you have di of u v nu I over d sigma. This is the birth. But what is di of u nu I? Our summation, this is nothing but your normal derivative, d nu, normal derivative. Okay. You have your that one. So, that you have your formula. So, this is nothing but integral of du by d nu v d sigma over the boundary of omega. Again, remember this formula, do not even spend time to recall, it should be there in your mind all the time. Okay. So, you have that formula plus gradient of u, gradient of v. Okay. So, and this gradient of u, you already know it, di of u, d1 of u, etc., dn of u. So, you have that formula. Okay. And then you can interchange u and v and subtract, interchange u and v and subtract. When you interchange u and v, grade u dot grade v will not change it. So, this may be an identity. In fact, this identity we have used even in the first course on partial differential equation. U Laplacian of v is equal to integral du by d nu v minus u dv by d nu. You see, so your surface integral is basically volume type integral is becoming a surface integral. So, you have your, and maybe one last identity before we conclude. So, use a different color so that it can, I do not want one more page coming here. So, So, suppose u bar I am applying to a vector now u1 etc. un, and this belongs to h1 of omega. Each component is belongs to h1 of omega. So, we can apply 1 to ui and sum it. These are all, again this equation may be useful if you do some Stokes systems. So, what you will get is that, so you go back to the first equation. So, if you go back to the first equation, if you have, so you have your di of ui, that means dui by dxi, and sum it, and that is nothing but your divergence. Okay, so you will get, this will imply integral over omega divergence of u bar v is equal to minus integral of u bar gradient of v. Yes, gradient of v and plus u bar, and then ui vi will come when you sum it, that will be u bar dot nu v d sigma. Okay, so that is correct. When you apply u, yeah, that is correct. So, you see you have one more formula useful in Stokes systems. In particular, as a last comment, in particular, if omega is bounded, then v identically 1 is in H1, and that will imply integral of omega, the divergence of v bar is equal to integral of u bar is equal to u bar dot nu, okay, over d omega. You will see again when you study Stokes system, how do you solve divergence to u bar is equal to the boundary equal to 0. You want to solve the equations like divergence of u bar equal to 0 with u bar equal to g on the boundary, leading to some compatibility conditions. Okay. So, these couple of few identities you can, so basically it is the integration by parts, and then play with this integration by parts, and this is the famous Gauss divergence theorem. You see, this is omega to boundary, this is the Gauss divergence theorem. So, I will stop here. These reviews, in the next class we will do some identities and some estimates and little more on your embedding theorems. Probably if everything is not covered, trace theorem we explained in detail, many embedding theorem you have seen, but let me recall a little more together with some identities which again will be using in the sequel. Thank you. Thank you.